In this video, we'll be discussing one-to-one functions and using algebraic proofs to determine whether a given function are one-to-one or not. Well, a function f of x is one-to-one if for x1 and x2 in the domain of f. If x1 doesn't equal x2, then f of x1 won't equal f of x2 either. Equivalently, if f of x1 doesn't equal f of x2, then x1 won't equal x2 either. That is, no two inputs map to the same outputs. The graph of a one-to-one function has to pass both the vertical and horizontal line tests. Now, we could certainly use that technique to determine whether these functions are one-to-one or not, but we just want to learn something new. We're advancing in our math, so we want to do more than just look at a picture to get an answer, and we're going to write a real proof. The proof technique that we're going to use is proof by contrapositive. This is a technique used frequently in math where if you assume the opposite, you prove the opposite of what you're actually trying to prove. I know that sounds crazy. All right, so a one-to-one function, it says that if f of x1 is not equal to f of x2, then x1 won't equal x2 either. What we're going to do is we're going to assume that f of x1 does equal f of x2. And then we're going to see if we can prove that x1 equals x2. See, so we're just doing the opposite of both. Instead of not equal to, we're going with equal to. And if we can prove that x1 equals x2, then what we have is a one-to-one function. But if the algebra doesn't work out, that we get that x1 equals x2, well then it's not a one-to-one function. All right, so let's see how this works. We're going to use this proof by contrapositive to determine whether or not f of x equals x plus 2 is one-to-one. Now, you probably already know the answer to this, because if we think about what the graph of this looks like, this is just a line with a slope of 1 and a y-intercept at 2, and we can certainly see that that's going to pass both the horizontal and the vertical line test. So we should get an answer of yes here, but let's see how to do it with this proof. All right, so we're going to assume that f of x1 does equal f of x2. And then we're going to try to show that that leads us to x1 being equal to x2. All right, so here goes. We're starting with f of x1 equals f of x2. Being that our function f of x equals x plus 2, we're going to plug in and now have x1 plus 2 equals x2 plus 2. I'm going to subtract 2 from both sides, totally legal math move, and that's going to leave us with x1 equals x2, which is what we were trying to show. So we started with f of x1 being equal to f of x2, and from that we were able to show that x1 equals x2. Therefore, we have a one-to-one function here. But now, since we're writing a proof, we actually have to put in a wrap-up statement. So here's the beginning of our proof that we've written so far, but now our wrap-up statement, we want to say therefore. So we'll use our 3 dots in a triangle to represent therefore. Therefore, f of x equal to x plus 2 is a one-to-one function by the contrapositive. And then at the end of every proof, you want to indicate that you're done. So either put in a filled-in rectangle, or you can use the three letters QED, which is Latin for quid erat demonstratum, just says, I showed you what I said I was going to show. All right, let's try another one. This time we want to determine whether or not g of x equals the absolute value of x minus 1, whether that's 1 to 1. And we'll use this contrapositive technique again. We're going to start by assuming that g of x1 is equal to g of x2. And we want to try to show that it would follow that x1 would be equal to x2, because if it does, then we know we have a one-to-one function here. Okay, let's start with g of x1 being equal to g of x2. Plugging that into our function, g of x equals the absolute value of x minus 1. That gives us the absolute value of x1 minus 1 equals the absolute value of x2 minus 1. I'm going to add 1 to both sides. That gives us the absolute value of x1 equals the absolute value of x2. And now we're going to have to apply our property of absolute value equality. If two absolute values are equal to each other, then their insides are either exactly the same or one is the opposite of the other. x1 would be equal to negative x2. So we worked out the algebra and we got more than just x1 equals x2. All right, what we were trying to show was x1 is always going to be equal to x2, assuming that g of x1 was equal to g of x2, but what we came up with is that they might be equal or they might be opposites. So because we got this extra over here that we don't really want, that means that this is not 1 to 1. So we'll write our wrap-up statement. Therefore, g of x equal to the absolute value of x minus 1 is not a one-to-one function by the contrapositive. And we know if we graph this would definitely fail the horizontal line test, as the graph here would be a V shape that has been shifted down. It's just nice to support our proof conclusion with something that we already know.